So now I want to introduce you to a new way to describe shapes in 3 dimensions, and that's using vector-valued functions. So instead of using equations in rectangular or cylindrical or spherical coordinate systems, right, we're going to use vectors to describe, right, what happens to our graph in the x direction, in the y direction, and the z direction independently, right, separately. So these x sub t, y of t, and z of t, these are the components. Right, notice I've used my vector notation. T is our parameter, right? T is going to be the independent variable. Sorry, the dog decided to play right now. So T is our independent variable. So the domain, right? Domain is the set of allowable t values. And it doesn't have to be a t. It can be a theta. It could be an x, right? You can parameterize using any letter. T is just really common. Okay? The range, right? So the output of these vector-valued functions, right, is the set of the position vectors you get when you evaluate R at the different t values. Right, so it's actually the set of vectors. Now, when we think about a graph of a vector-valued function, typically what we're thinking about is a trace of those endpoints of your position vector R's. Okay, so let's just practice. Let's find the domain. So determine the domain for these 2 functions. So my first function R is e to the t, right, so the x part, the y part, cosine t, and the z part, 1 over square root t. So domain restrictions, these are the same that you've had all along since you very first started talking about functions, right? The things you have to be careful of, can't divide by 0, right, so no division by 0. Square root of, right, the radicand has to be greater than or equal to 0. And the other common one that comes up is natural log, right? The natural log of t. T has to be greater than 0, can't be equal to 0. Okay, so if I look at my first one, e to the t, that has no restrictions, so that one is going to have all real numbers. Cosine t, again, you could take the cosine of anything. That has a domain of all real numbers. My z component, though, it does have some restrictions, right? So that last one is going to limit everything to t's only greater than 0. So I won't say greater than or equal to, because if I had let it equal 0, then I have the divide by 0. So my domain for all of R would be t's are greater than 0. Okay. So for the second one, R of t, so my x component is the constant 5. Okay, that doesn't have any restrictions. The y component, cosine squared t, again, take the cosine of anything, square it, that's fine as well. That last one, now I have the natural log of t minus 3. Can only take the natural log of values that are greater than 0. So we're just going to grab that argument of your natural log, t minus 3 greater than 0. Solve for t. And so t is greater than 0 is that domain. So this is this set. So you could use some set builder notation. You could use interval notation, however you want. I'm kind of being lazy and just writing it like that. So another thing we might have to do is evaluate a vector-valued function. So this time my vector-valued function is t squared, and sine pi t. So can we evaluate this function at 1, at 2, and at 3? Right? So R of 1, what is that vector? So it's 1 in the x direction, 1 squared, that's also 1, and the sine of 1 pi. Okay, well, what's the sine of pi? 0. Okay. R of 2. Okay. So I get t, so 2 squared, 4, and the sine of 2 pi. Oh, sine of 2 pi, that's 0 as well. So 2, 4, 0. Not all of your z values are going to be 0. It's just that I'm going in integer pi's, so those will all be 0. That's okay. So R at 3, So 3, 3 squared, and then the sine of 3 pi. And the sine of 3 pi is, again, 0. Okay, let's do one more just so that you don't think they're always going to be 0. So let's do r of, how about 1/2? What do we get for that? Right, so my first one is t, so right, what you put in, you get out. Second one, t squared, so 1/4. Z part, sine of pi times t, so that'll be pi halves. And the sine of pi halves is 1. So this vector is 1/2. 1/4, 1. Okay. So, right, just like when you first began graphing, right, you'd start by making a table of values. So we could try to plot these vectors, and we'd want to get some in between so that we didn't think that my z value was always 0 and that I was only in that xy plane. Okay. All right, well, let's go ahead and let's try graphing something that's hopefully a little bit easier than that. Right, so my first one that I want to try to graph, I have 4 cos t, 4 sine t, and 3. So we have to recognize this from our parametric lives before. So if you know that x equals 4 cos t and y equals 4 sine t, what does that, right? It's super helpful if you kind of know going in what this is a graph of or what this represents. Right? So this is our circle, radius of 4, and then the center is going to be right at x equals 0, y equals 0, right? So it isn't displaced at all. And then what about that z value of 3? What is that going to be? Okay. So if we want to think about this, so let's just do that first one. Let's make a quick little table of values. So we'll do t and we'll do x. I'm just going to do x and y because that z is a constant 3, right? So it's not going to change. Okay, so let's see. T can be anything. I'm going to go ahead and just stay positive. So we'll go 0, and then how about pi fourths and pi halves, just to kind of get an idea of where it's going to go, and then pi. Okay. So I'm looking up here at 1. So if t is 0, my first one, cosine of 0 is 1 times 4 is 4. Sine of 0 is 0 times 4 is also 0. Pi fourths, so that's going to be 1 over root 2, so I'll get 4 over root 2 and 4 over root 2. Again, my z value is constantly 3, so I don't need to write that one down. At pi halves, now my cosine is 0, right? And my sine is 1, so that'll be up there at 4. And then at pi, so swooping all the way around, here, let's stick in a 3 pi fourths just to make sure, and then we'll end at pi. See if that gives us enough of a knowing what's going on. So 3 pi fourths, so over on right quadrant 2, cosine is negative, so that'll be a negative 4 over root 2. Y is still positive, 4 over root 2. And then at pi, cosine of pi is negative 1, so that'll be negative 4. Sine of pi is 0. And then again, my y value is 3. So my y values are staying positive. My x's go from positive 4 to negative 4. I bet if I take a few more t values here, I'll get those negative y values as we swoop back around. Right, so if I graph that first one, and I'm just going to do, right, so here's my x, y, z. So I start out here at 4, 0 from the y, and then I'm going to move over here into this first octant, and then 0 to 4, right? Here's 0, 4 on the y-axis, right? And then my x goes negative, but my y is still positive, so I'm kind of swooping back here around. Right, so it's going to be this circle. Oh my gosh, and me and my drawing. So that's going to be a circle, but then I have to lift it up 3. So I'm just going to go up 3 on the z-axis and then draw that circle of radius 4. Okay. So what's happening, right? So this is the trace that I was talking about, the tips of those vectors. What we're really doing, though, is those r vectors, right? So here is the r when t equals 0. right? We start at, oh, sorry, that was over here. Here's my R of 0, starting at, right, the point 403. This one over here, when I had my Y of 4, so 0, 4, 3, right, that point up here, 0, 4, that was when my T was pi halves. Okay? So I'm going, starting here, and then moving in this direction. So these vectors are just swooping around and tracing out this circle, right, that's up 5. Okay, let's take a look at number 2. I'll copy it down here. I'll grab a new color. So vector 2 is a very important one, and this is a helix vector that I'm not going to, well, I say I'm not going to try to draw it, and then you know I am, and it's going to be painful, but there you go. So if we think about what's happening for our x value, right, the x component, that just matches whatever your t is, right? So as t gets bigger, your x gets bigger. But the y and the z, right, this is our circle, right, parameterization, right? So these two together, we get circles in the yz plane. And then in the x direction, right, it's just marching on. So I want you to think about, right, if you have circles in the yz plane, but the x is just marching on, it's like a slinky. Okay? So this is one way to describe, and it's called a helix. Okay, so if you in a biology class, right, DNA, the double helix, that's going to have, right, equations like this. If you have that toy from a retro shop, it's what a slinky looks like. It's a helix. Okay. So if t is 0, x is 0, cosine of 0 is 1, sine of 0 is 0. If we go out to pi fourths, right, x is moving along at pi fourths, cosine of pi fourths, 1 over root 2, sine of pi fourths, 1 over root 2. At pi halves, right, x is moving along, pi halves, right, so we're kind of marching out the x-axis as this circle is spiraling along. Cosine of pi halves, now we're back to 0, sine of pi halves, we're up to 1. Okay. So it's this slinky, and it starts at here, and then it's going to go up, and it's kind of coming out the page along the x-axis.